Monday, we switched from talking about, we've talked about the number of possibilities of things happening, like the number of combinations of donuts or ways that you could have Chipotle or whatever it might be. And we kind of switched gears a little bit and we started talking about probability, which has to do with the number of possible options, right? Because we need to know that if you're trying to find the probability of something happening, you need to know the total number of possible outcomes. So, how many possible combinations of donuts are there? What's the probability that you would pick one that's chocolate? So we would have all the ones that are chocolate on the top and then all the possible donuts on the bottom, right? So we talked about that. And then we also, at the end of class, we talked about the odds. So the odds are a little bit different than probability, right? So the probability is the number of favorable outcomes to the total number of outcomes. So a really simple probability problem that most people can visualize is what's the probability that you would roll a 1 on your dice, and there's 6 sides, so there's 6 possible outcomes, and there's only 1. So there's a 1 in 6 chance that you'll roll. There's a 1 in 6 probability that you'll roll a 1, or there's a 1 in 6 probability you'll roll a 5, or any of those, right? At the end of class, we talked about odds, and odds are calculated a little bit differently. So you see here, and it's kind of flip-flopped, but if you have the odds in favor of something happening, that's the probability of success divided by the probability for failure. Okay, and then the probability of against is just the opposite, that failure to success. And I was trying to come up with some examples for you guys of odds that weren't betting, but I at least came up with one from, I was reading Around the World in 80 Days with my son, and they were talking about, there's a gentleman that's trying to go around the world, and they were talking about people placing bets on him. And so they were saying the odds were 1 to 10 or 10 to 1, then 20 to 1, then 100 to 1, then 200 to 1. So, and even in this, old classic book, they were talking about betting with their odds. So that's kind of the difference between the two. And I think everybody kind of got that on Monday. All right, so today what we're going to talk about is the probability of disjoint and overlapping events, okay? So we have a couple things here. We have mutually exclusive events, inclusive events, or both things that will happen. So let's kind of jump in with some examples here and talk about how this works. We get to bust out some Venn diagrams today too. Yay. Okay, did I just do that wrong? Hold on. All right, here we go. All right, so if we are talking about two mutually exclusive events, so mutually exclusive means that that one of the events does not depend on the other event. All right, so there's not an interdependency between the two. So we're talking about basically, well, let's talk about in a problem down here. All right, so if you pick one card from a deck of 52 cards, what is the probability of selecting an ace or an 8? Okay, so the key thing that I want you to notice here is that, first of all, this is an or, right? It's not an ace and an 8 because that would be something different. But what is the probability that you will pick out either an ace or an 8? Okay, so does picking one or the other one depend on each other? Could you pick an ace and an 8, I guess is my question. Like if you're picking one card, could it be an ace, both an ace and an 8? No, right? It just either has to be an ace or an 8 when you're picking one card from the deck. So the probability of picking an ace, I'm going to do this. Probability of an ace and the probability of picking an 8, right? They don't depend on each other. So if you're trying to find, this is an example of something that's mutually exclusive. If you're trying to find the probability of that, then what you do is you add together the probability of the first event and the probability of the second event. So what is the probability out of 52 cards that you will pick an ace? Gotta script over for the chat. What's the probability you'll pick an ace out of 52 cards? All right, I'll give you guys this one. It's 4 out of 52, right? Just the probability you'll pick an ace is 4 out of 52 or 1 out of 13. We talked about this on Monday, right? There's a 1 out of 13 chance you'll pick an ace. Okay. What is the probability then that you will pick an 8? E-I-G-H-T. What's the probability you'll pick an 8? It's also 4 out of 52 or 1 out of 13, right? So then what is the probability of selecting? You're just picking one card. So this isn't, you're picking one card. What is the probability that card would be an ace or an 8? So in order to find out what's the probability that either an ace or an 8 will get picked, we're going to add the two probabilities together. The probability of an ace plus the probability of an 8, which would be 1/13 plus 1/13 equals 2/13. Right? You have a 2 out of 13 chance of picking an ace or an 8. Now, you might have just been able to do that without doing this math here. You might be able to think in your head, well, in 52 cards, 8 of them are either aces or 8s. So 8 out of 52 means 2 out of 13. I understand that. But I just want to show you that's how you mathematically do that. Those are called two mutually exclusive events, right? So picking A doesn't depend on what happens when you pick B. Does that make sense to everybody? Are you guys awake? All right. Olivia's awake. She said, yeah. All right. And Noah. All right, cool. You guys are with me. All right. So that's good. We know how to do that. It kind of makes sense even if you don't know the formula, what you would do. So then what happens when I erase all this, get rid of all this messy handwriting? Okay. What happens if you go to pick a card? What is the probability that you will pick a 10 or a diamond? A 10 or a diamond. Dun, dun, dun. All right, so the reason I said dun, dun, dun is because one of the cards is a 10 of diamonds, right? So you could pick a 10 of diamonds, or you could pick a 10 of hearts, or you could pick a 3 of diamonds. All of those would be counted as choices. So this idea that some of your choices are exclusive of each other, but there is one card, the 10 of diamonds, that belongs to both probabilities, means that this is something that's inclusive, a probability that's inclusive. Okay? And so how do we do a probability problem like that? So I'm going to try to do this visually and mathematically so you can kind of see. All right? So what is the probability that you will pick a 10? Probability that you will pick a 10. So we're going to just look at this part. What's the probability out of a deck of 52 cards that you will pick a 10? It's 4 out of, yep, exactly. 4 out of 52 or 1 out of 13. Thanks, Leah. Okay, that's the probability you'll pick a 10. What is the probability that you will pick, try to draw a nice diamond, a diamond. What's the probability you'll pick a diamond? So this one's a little different. There's 4 suits in a deck, right? What's the probability we'll pick a diamond? There's 13 cards in each suit out of 52 possible cards, right? So the probability you'll pick a 10 is 1 out of 13. The probability you'll pick a diamond is 13 out of 52. So what's the probability that you'll select a 10 or a diamond? Okay, so I could say that the probability that I'll pick a 10 or a diamond is, and I'm going to stick with my larger fractions since they add together, is 4 out of 52 for my 10 plus 13 out of 52 for my diamond. And if I add them together, I get 17 out of 52, right? So that seems right, but there's one last piece that kind of is going to trip us up, and that's this guy, the 10 of diamonds. 10 of diamonds, right? Because we counted the 10 of diamonds in this group of probability, and we counted the 10 of diamonds in this group. So we basically have double counted the 10 of diamonds when we did this probability. That makes sense? We've let the 10 of diamonds get double probability counting. That's probably not mathematically correct, but that's basically what we've done. We've counted it once here, and we've counted it once here. So what we have to do is we have to subtract out the probability that both will happen, the probability of a 10 and a diamond happening. Okay, so really, if I drew my diagrams like this, the circle should actually be bigger for each of these. And I'll try to erase the other circle here. Yep. So really the circle for each of these should be bigger. And, sorry, this works better on a whiteboard. Really the circle should be bigger for each of them. And that 10 of diamonds should go in here, right? Because it's counted in both of those. So what is the probability of getting a 10 of diamonds? We're going to take that, a 10 and a diamond, and that is 1 out of 52. There's only one card that's a 10 of diamonds. So we have to subtract that out of our probability because we basically have double counted it when we just add those two together. So really the probability of getting a 10 or a diamond is 16 out of 52, which is about 0.31. So there's like a 31% that you'll pick a 10 or a diamond out of your deck. Okay? Does that sort of make sense? Definitely make sense? Not at all make sense? All right, I'm going to assume you guys are good. So, cool. Awesome, thanks. All right, so let's try the next problem. Sounds exciting, right? All right. I think I have a typo in this one, but you guys will get the idea. Okay, here we go. There are 200 students. 64 are either in the band or on the honor roll. Okay. 32 are in the band, 51 are on the honor roll. What is the probability of a student being in both the band and, I don't know why they're in the atrium. I should say honor roll. Question mark. We'll just replace that. All right, so there's a whole lot in this. All of a sudden it's like, what, huh? Okay, so what I like to do is break it down into parts, okay? There are 200 students, so that's your whole population, right? That's your total number of students. So let's skip the first part. It says 32 are in the band. Okay, so the probability that you're in the band is what? The probability that you're in the band is 32, because there's 32 students, out of how many total number of students are there? $200. Thank you. And actually, I'm going to take a step back. Before I start filling in all these things, let's think about the bigger picture of what this question is. And that's kind of like what's at the top of your page. So the question is, what is the probability of a student being both in the band and on the honor roll? Okay. So we're going to use this idea of inclusive events. So what this looks like is it looks like the formula that's at the top of your notes. So I know I kind of launched right in, but I want to make sure that we get big picture first before I launch right in. Okay. So we will actually have the probability that you're in the band or on honor roll, right? Because you could be both, equals the probability that you're in the band plus the probability that you're on the honor roll minus the probability that you are in band. Make this bigger. And honor roll, both. So do you understand? There's some students that are just in band. There's some that are just in honor roll. There are some that are both in band and honor roll together. So those actually overlap. The people that are in band and the people that are in honor roll would overlap with the people in band and honor roll, right? And then that added together is the people that are in band or honor roll. Okay, so now I'm back up here. Leo, help me out. The probability that you're in band, since there's 32 students in band, the probability you're in band is 32 out of 200. What is the probability that you are on the honor roll? Well, there's 51 students, right? Out of 200 are on the honor roll. So the other piece of information, if we go back here, is read this. It says 64 students are either in the band or the honor roll. So what they're giving you is this. They're giving you the probability that you're in the band or honor roll, right? So what is the probability you would be in the band or honor roll based off of this? It would be 64 out of 200, right? And then the question is, what is the probability of a student being in both the band and the honor roll? So what you're trying to find is both the and, which is this, band and honor roll. That's what you're trying to find, right? So then it just becomes a mathematical problem. We just got to plug in what we know. So we know that the probability that you're in band or honor roll is 64 out of 200 equals the probability of band, which is 32 out of 200, plus the probability of honor roll, 51 out of 200, minus, and we're just going to call this, well, we'll write it up. Probability of, I'll just say B and HR, band and honor roll. Okay, so then if you do the math, thankfully they all have the same denominator for your fractions, right? So we're able to move them around. So 64 out of 200 equals 83 over 300 minus, sorry, that's a minus, minus probability of band and honor roll, right? Then you're going to subtract this 83 over 300 from both sides, minus 83. Oh, sorry for the crazy writing. Like, ugh. So what do you get when you subtract that? You get 19 out of, oh, all of a sudden I turned into 300. 19 out of 200. Sorry, this is 200s. We didn't somehow get 300 students. 19 out of 200, right? So what is the probability that, and sorry, this is going to be negative, and then this is a negative over here. So they're going to cancel each other out. Band and honor roll. This is so messy. All right, so the probability that someone would be in the band and the honor roll is 19 out of 200, otherwise known as, it's about 9.5%, if you want to think of it that way. Okay, how did everybody feel about that one? Okay. Maybe at the end I'll find another one from your homework and make sure that we got that one. So sometimes you'll have that overlap and sometimes you won't, right? Okay. I'm going to tell you one other thing that you can use when you find the probability of something. Okay. So this is called the complement of an event. And I actually don't like what my note says right here because it doesn't really make sense. But sometimes instead of finding the probability that something is going to happen, it's easier to find the probability of the opposite and then subtract from one. Okay, so let's just think about this. Actually, I'll open that, but I'm going to do something off to the side. Okay, so if you wanted to find, and this is a super simple example, so I wouldn't necessarily use this theory, but this is the very general theory. Okay, if I wanted to find the probability that you're rolling one die, you're rolling the dice, and I wanted to find the probability that you how do I want to say this? I wanted to find the probability that you do not roll a 6. Okay. What is the probability that you do not roll a 6? Well, when you roll the dice, in theory, it should be even, unless Aaliyah has another interesting fact for us, right? In theory, it should be random when you roll your dice, which I believe you, Aaliyah, on the coin toss. But when you roll a dice, what's the probability you won't roll a 6? Well, you could roll a 1, 2, 3, 4, or 5, and those are all not 6s. So there's 5 out of 6 ways that you would not roll a 6, right? You could roll 1, 2, 3, 4, 5, and those are all not 6. Okay, so that's, I think everybody kind of gets this. Another way that you could calculate the probability that you do not roll a 6 is you could use something called the complement. Okay, so the complement means that you take 1, the number 1, and you subtract the probability that the event does occur. So instead I could say 1 minus the probability that I do roll a 6. All right, so 1 minus the probability I do roll a 6, the probability I do roll a 6 is 1 out of 6. And so if you do this math, you end up with there's a 5 out of 6 chance that you do not roll a 6. So this is a pretty simplistic example, but it just shows you that it's that probabilities are complements of each other, right? The idea of not rolling, if you have a 5 in 6 chance of not rolling a 6, that means you have a 1 in 6 chance of rolling a 6. So the two probabilities of something happening and not happening always add up to 1. So we can use that knowledge to basically use the complement of something. Sometimes it's easier to figure out the not of the event occurring than to figure out if it is occurring. And that'll make sense when we're doing the problems. But I just wanted to show in a simplistic way why it works, right? And this is only so we're kind of switching gears a little bit. This isn't talking about, ace or eights or band or honor roll, like 2 events occurring. This is just talking about using the idea that probability always adds up to 1. So sometimes it's easier to calculate probability problems by using what we call the complement. Okay. And again, I know this is simplistic, but gives you the idea that it works both ways, right? Okay, so let's take an example where it might make a little more sense to actually figure out what the complement is. All right, take that off there. All right, so you're going to roll 2 6-sided dice. So you're going to roll the dice. And what is the probability that the sum is not 6? Okay, so you're going to roll the dice. You're going to roll 2 dice. And what is the probability that the sum is not 6? So is there going to be a lot of, well, I guess how many combinations are there of rolling 2 dice? How many different possible outcomes do we have? So when we roll the first dice, there's 6 possible numbers. And when we roll the second, there's 6 possible numbers, right? So when we roll 2 dice together, we have 6 times 6, we have 36 possible outcomes, right? Some of those are duplicated. It's okay that they're duplicated, right? We just have 36 possible outcomes when we roll the dice. And that's back to what we talked about with the Chipotle problem with our fundamental counting principle, right? First dice has 6 possibilities. Next dice has 6 possibilities. So 6 times 6, there's 36 different possibilities for adding 2 numbers together, right? Do you think there's going to be more cases where the sum is 6 or more cases where it's not 6? Yeah, there's not very many that will equal 6, right? So the reason I was asking that, Anton, is because it's, for this case, finding the probability that it's not 6 is going to be a lot of numbers. So it might be easier for us to find the complement and say, well, that's equal to 1 minus the probability that we do get a 6. So if we find all the ways we could get a 6, then if we find all the ways we could get a 6 and then we subtract 1 from that, or we subtract that fraction from 1, then we'll get all the chances that we do not get a 6. Okay? So let's figure out what is the probability that I will roll a 6, because that's going to be a much smaller number than I won't roll a 6. Probability that I roll a 6, right? So there's 36 possible combinations. What are all the combinations that I could come up with to roll a 6? So I could get a 1 and a 5, right? A 2 and a 4, a 3 and a 3, right? I could also get a I could also get a 5 and a 1, a 4 and a 2, and I could get another 3 and 3. Right? Those are all the ways that I could roll a 6. So what is the probability that the sum is not 6? That would be equal to, there's a probability that I roll a 6 of 6 out of 36, right? The probability I don't roll a 6 is 1 minus 6 out of 36, or 30 out of 36. I guess I should show you how I did that math. Whenever you have 1, it's super easy to change it into a fraction. So since this denominator is 36, you're going to turn 1 into 36 over 36 minus 6 over 36. So it's going to be 30 out of 36 chance that you do not roll a 6. Right? And I think your book actually has a nice little chart that shows all of the options for rolling 2 sets of dice. Actually, let me see if I can pull that up online really quick. All right, 2 rolling 2 dice chart. Is this what I want to look at here? I thought I was calculating that off. There's actually only 5 possibilities for rolling a 6. That's why I wanted to pull up the chart. I was like, I think there's only 5. I have 5 written down. So if you roll, Anton, did you catch this for me? If you roll 1 dice and 1 dice, I shouldn't have counted the 3 twice. So you can do 5 and 1, 4 and 2, 3 and 3, 4 and 2, 5 and 1. So I shouldn't have counted that twice. There is still 6 by 6. There's still 36 possibilities, but only 5 of them roll a 6. So by the magic of the eraser, I felt like that was wrong when I was saying it. Should have trusted my math gut. And this chart does exist in your book, by the way. So there's a 31 out of 36 possibility that you will not roll a 6. All right, let's use the chart for the next one and make sure you use it for your homework because obviously that helps a lot. All right, so next one. What is the probability that the sum of your two dice is less than or equal to 9? So B is, what is the probability that the sum of your two dice is less than or equal to 9? Okay, so if I looked at my chart over here, right, what is the probability that the sum of my two dice is less than or equal to 9? So basically what I'm looking at here is all of the numbers from here over. What is the probability that is less than or equal to 9? It's going to be all the 9s, 8s, 7s, 6s, 5s, 4s, 3s, or 2s. So you could actually just look at this chart and add it up because it's not that many numbers. But since we're talking about using the complement, we'll go ahead and do that. So what we could do instead is we could instead say, well, that's equal to 1 minus the probability that the sum is greater than 9, right? And that's a smaller number that we have to count. I guess it makes it a little bit easier, right? So if we have 1 minus, what is the probability the sum is greater than 9? Well, we have 1, 2, 3, 4, 5, 6 instances where the sum is greater than 9 out of 36 total outcomes. So this is probably the one I was thinking of, is 6 out of 36, which does work out to be 30 out of 36 probability that the sum is less than 9. Okay, and then if we go back here and we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. There's 30 possibilities that it's less than or equal to 9. Okay? So that's a way that kind of make it easier for that. I'm just looking here. I have this fortune cookie problem, but let me grab my book really fast. I think I want to do one from your homework versus the fortune cookie one. We can do that one. So while I grab my book, look at this one and see if you can think of how you might solve number 4. But give me like 2 minutes. Well, maybe 1 minute. I'll be right back. Okay, I'm back. Did anybody figure out number 4? A restaurant gives a free fortune cookie to every guest. They claim there are 100 different messages hidden inside the cookies. What is the probability a group of 5 people receive at least 2 fortune cookies with the same message inside? It's like a big jump from where we were. Anybody figure it out? All right. Well, instead, I want to make sure that I don't think you have any homework problems like the fortune cookie one. If we have time after we finish up, we can do that one. Do you guys feel more comfortable with the idea of doing the complement? Actually, there's not a whole lot of complement problems. They're more of the this disjointed or the inclusive events. I'm just looking through your homework here to see which one we want to do. All right, so for example, if you were doing number 25, I'm on page 710 of your book. Okay, number 25 says, a card is randomly selected from a standard deck of 52 cards. Find the probability of drawing the given card. So what is the probability of, this is number 25. What is the probability of not drawing a heart? What is the probability of not drawing a heart? So if you had to do number 25, what do you think you would do? Do you think you would calculate the probability of drawing a heart and then find the complement of that? Or do you think you would just find the probability of not drawing a heart? Either one would be not too bad to do. So think about it. The probability of not drawing a heart means that you would draw a a diamond, a club, or a spade, right? So there's 13 diamonds, 13 spades, and 13 clubs out of 52 total cards. So there's 39 out of 52 possibilities, which actually boils down to there's a 3/4 possibility that you will not draw a heart, right? Or you could do the probability that you will not draw a heart is equal to 1 minus the probability you will draw a heart, right? Which is 1 minus 1/4, because there's a 1/4 chance you'll draw a heart, which equals 3/4. So either way would be acceptable ways to do that. I did not specifically tell you guys this, so when we want to know when you get to 17 and 19, the idea of the complement is written like this. So if you have, and that's why it's not in your book, it kind of looks funny. Or in your notes, it kind of looks funny. But if you want to find the complement of something, it's written like this. So if you have the probability of an event happening that you want to use the complement, it's written like this. So this is the idea that the probability of not drawing a heart is equal to 1 minus the probability of drawing a heart. So the little line over the A in this case would indicate that that's the complement of an event. So we say A bar. All right. I think you guys should be able to tackle everything. I'm just looking through your homework just to make sure. I think you should be able to tackle everything. What we're going to talk about on Monday is, so that was like the or events, the probability of a ace or a 10, right? What we're going to talk about on Monday is we're going to talk about either independent events, what the probability of that is, or also dependent events, so one that depends on the other. So we will talk about that on Monday. Thanks, guys, for coming. I'll stay on if you have any questions. If not, I will see you on Monday, and have a good week.